Hi, now we are analyzing CSIR June 2011 Chemical Sciences. Just look at the given problems. According to crystal field theory, nickel plus 2 can have two unpaired electrons in octahedral, square plane or tetrahedral, both octahedral and tetrahedral geometries. Okay, we know that in nickel plus 2, 8 electrons present in its d orbital. In the absence of ligand field effect, the d orbital of nickel is simply considered as degenerate d orbital. Okay, right. In the presence of ligand field, the degenerate d orbital splits into different energy levels based on the approach of ligands. Okay, for example, if we consider octahedral geometry around nickel plus 2, the degenerate d orbital of nickel splits into T2g ground state and Eg excited state. Okay, and in T2g we know that we have 3 suborbitals, and in Eg we have 2 suborbitals, and each suborbital can fill maximum filled with 2 electrons. Okay, right. So here we have 8 electrons. In T2g we can see 6 electrons, and in Eg we can see 2 electrons. Okay, here the 2 electrons in Eg level are unpaired because we have 2 unpaired electrons in 2 suborbitals of that nickel plus 2 octahedral complex. And if you go for tetrahedral geometry, here Eg is ground state and T2g is excited state. Okay, just fill the electrons according to Hund's rule, and you can see that here we have 2 unpaired electrons in T2g. Okay, and whereas if you look at a square planar geometry of nickel plus 2 complex, then the ground energy state is dxz dyz followed by dz square followed by dxy followed by dx square y square. So this is energy increasing to those orbitals. Okay, right. And just fill the electrons according to Hund's rule. You can simply get that all the electrons are paired up in different energy levels, the different suborbitals according to the energy of the square planar complex. Okay, and now by just observing this, you can say that octahedral, tetrahedral geometries of nickel plus 2 having 2 unpaired electrons. Okay, next question we have given with 2 nickel complexes with the first one with cyanide, second one with chlorine as ligands. Okay, both diamagnetic, both paramagnetic, dia and paramagnetic, and fourth one is antiferromagnetic and diamagnetic. Okay, yeah. Now so just try to check the nickel acceleration state here in the first complex. So here nickel plus 2 acceleration state, and in the second one also nickel is in plus 2 acceleration state. Now here, due to the effect of nitrile or cyanide ligand, we know that cyanide is a strong ligand according to spectrochemical series. Okay, whenever strong ligand is present, then what is just happening? Simply these 2 electrons are simply paired up. Okay, that means the electron moves into other suborbital to make it pair. Okay, and that's why we can see that means 0 unpaired electrons. Okay, so whenever 0 unpaired electrons are there, it is simply diamagnetic in nature, right? And if you look at nickel tetrachloride, in nickel tetrachloride, chlorine is a weak field ligand. That's why here no pairing up of electrons takes place, and that's why 2 unpaired electrons can be observed for nickel tetrachloride, where nickel is in plus 2 acceleration state. So whenever unpaired electrons are present, it is simply paramagnetic in nature. Okay, that's why here due to the effect of ligands, here the first complex is diamagnetic due to absence of unpaired electrons, and second one is paramagnetic due to presence of 2 unpaired electrons. Okay, right. And next question, which of the following spectroscopic technique will be useful to distinguish between MSC and MNCS binding modes? Okay, simply if you look at the first one, whereas thionitrile. Okay, so in the thionitrile you can observe that C triple bond N, that means nitrile. And if you look at the second one, whereas isothionitrile, where nitrogen is coordinating to the metal, whereas in the first one sulfur is coordinating to the metal, and in the second case carbon and nitrogen having 2 bonds only. We know that whenever the number of bonds increasing, that's simply indicating that increasing bond order. Whenever bond order is increasing, then bond strength increases. Whenever bond strength increases, frequency increases. Okay, now just look at the first one. In between carbon and nitrogen, bond order is 3 when we compare with carbon and nitrogen here. Okay, so whenever bond order is 3, simply higher frequency is observed when we compare with the second one. Okay, whereas carbon and nitrogen having 2 bonds only. Okay, next one, which of the following compound shows a charge transfer band? So here we have given with lanthanum nitrate, ceric ammonium nitrate, manganese plus 2 acetate, copper plus 2 sulfate, pentahydrate. And if you look at the second, ceric ammonium nitrate, whereas nitrate is a bidentate ligand, here we have given with 6 nitrate ligands, so 6 into 2, 12. Okay, that means cerium is coordinated with exactly coordinated with 12. Okay, the coordination number of cerium is 12 here. Okay, and from that simply cerium is in +4 oxidation state. Okay, +4 oxidation state because each nitrate has -1 charge here, so total charge is -6, and here we have -2 total on the complex, because here we have 2 ammonium plus. Okay, so from that we can simply say that cerium is in +4 oxidation state, and whenever we see higher oxidation state on central atom or here a central element, then what is happening? Ligand to metal charge transfer is possible. Okay, ligand to metal charge transfer is possible, and here that's why ceric ammonium nitrate, due to the presence of highest oxidation state +4 on cerium, there is a possibility of charge transfer band. Okay, right. Next one, among SF4, BF4 minus, xenon tetrafluoride and ICl4 minus, the number of species having 2 lone pairs of electrons on the central atom according to Vesper theories. Okay, so we can use this method always. That is, we need to look for the central atom, that is sulfur, and it is having 6 valency electrons, and in those 6, 4 valency electrons are making sigma bonds with 4 fluorines, and here we have 2 electrons which are free. That's why we consider it as a 1 lone pair electron. Okay, so that's why, and just check this hybridization, sp3d. Okay, and sp3d here, sp3d with 1 lone pair electron. Okay, so just like by just using that, we can simply say that BF4 having 0 lone pairs, and xenon tetrafluoride 2 lone pairs, and ICl4 minus 2 lone pairs. Okay, so the question is the 2 lone pair electrons containing central atom. So in that case, xenon tetrafluoride and ICl4 minus are having 2 lone pair of electrons. Okay, right. Next one, the false statement for a polarographic measurement procedure is O2 is removed, dropping mercury electrode is working electrode, ID is directly proportional to the concentration of electroactive species, residual current is made 0 by adding supporting electrolyte. Okay, right, and just concentrate on polarographic measurement because we are getting frequent questions on polarographic measurements. Okay, yeah. Now O2 must be removed because it gives its own polarigram. So due to it can produce H2O2 and water molecules. Okay, that's why O2 must be removed in polarographic techniques. Next one, DME. Okay, so dropping mercury electrode is working as working electrode in polarography. Okay, and here ID is directly proportional to the concentration. And the fourth statement, that is residual current need not to be made 0 here in polarography. That's why fourth one is the correct answer for the given problem. Okay, next one, the ligand system present in vitamin B12 is simply choline, whereas choline contains a metal cobalt +3. Okay, which one of the following exhibits a rotational spectra? So here first we need to know the selection rule, that is, for rotational spectra, dipole moment must not be equal to 0. Okay, and if you look at all the 4 species which are given here, carbon monoxide has a dipole moment not equal to 0, but whereas here H2, N2 and CO2 both are all of them have dipole moment equal to 0. These two are homonuclear, and here is the presence of center of symmetry in carbon dioxide. That's why all of them have dipole moment equal to 0, whereas a heterodiatomic molecule CO doesn't have dipole moment as 0. Okay, so that's why here third option is the correct answer. Next one, in Ziegler-Natta catalyst, the commonly used catalyst system is, so titanium tetrachloride, triethyl aluminum. So this catalyst mixture is used in Ziegler-Natta catalysis. Next one, oxidation occur very easily in case of, so just try to check the total valence electron count on each of the complex. Here we have given, right, which are given here, and in that case the second one where you can count 19 electrons. Okay, we know that each NETA5 C5 H5 contribute 5 electrons, and here cobalt contribute simply 9 electrons. Okay, so here we have 2 NETA5 C5 H5, that means total of 10 electrons, plus from that cobalt 9 electrons, total 19 electrons. We know that a complex is stable whenever it has 18 electrons, okay, and which is following 8 electron rule. That's why, so it is ready to lose 1 electron. That means oxidation occur very easily in the second one to make it stable by just getting 18 electrons. Okay, just try to check all other three complexes. Okay, right. Next one, complex in which organic ligand is having only sigma bond with metal is. If you look at the first one, that is tungsten complex, where tungsten is coordinating with carbon directly. That means you can see here simply the sigma bond only present in that complex. Okay, that's why the first one is the correct answer. If you look at second one, third one, and fourth one, in second one, pi bond interactions are possible from that NETA5 C5 H5, and pi bond interactions possible from the benzene rings or benzene ligands. And if you look at the third one, whereas C2H4, here we have ethylene is connected with platinum here. Okay, that means simply G salt. Okay, so this is the structure of G salt, and where the pi interaction is there with the central metal. So the first one is the correct answer. And next one, in the molecules H2O NH3 CH4, bond angles are same, hybridization same, bond distance are same, shapes are same. Now look at bond angles of water 104.5, and ammonia 107 degrees, and here methane 109.5 degrees, and shapes water bent, ammonia pyramidal, and for methane tetrahedral, and hybridization is same, sp3 and sp3 for all H2O NH3 CH4, whereas bond length is decreasing from OH to NH, increasing from OH to NH and NH to CH, because just think that the whenever electronegativity of one of the atom is more, then bond, that means in bond interaction with other bonding atom is more. That's why here oxygen, hydrogen have less or the small bond length when we compare with NH and when we compare with carbon, hydrogen, because the electronegativity from oxygen to nitrogen to carbon decreasing. Okay, right. Next one, the correct order of stability of difluorides is, so here so correct order, to give the correct order we need to look at the CF2, in which fluorine, okay, so fluorine with a lone pair of electrons on it, and it is ready to back donate to that carbon. Okay, so that's why here is a formation of a double bond like interaction between carbon and fluorine, and here you can see the resonance stabilization. That means the charge stabilization can be observed. So that's why CF2 has the greatest stability when we compare with silicon difluoride followed by germanium difluoride. Okay, so second order is the correct one for a given problem. Okay, next one, the number of possible isomers for ruthenium complex, whereas we have given with bipyridine as a ligand and 2 chlorines. Okay, right, and bipyridines here, so we have two possible geometries, trans and cis. Okay, so this is trans, only trans form, one trans form can be observed, whereas if you look at the cis form, you can observe that those two cis forms are mirror image. They are enantiomers. Okay, so two enantiomers and one transform. So total three possible isomers can be observed for given ruthenium complex. Okay, next one, the species neon 19 and carbon 14 emit a positron and beta particle respectively. The resulting species formed are, so first one is from that neon nuclei, one positron is emitting. So positron expressed like this. Okay, so where whenever positron is emitting, it is giving, that means simply the atomic number increased by 1. Whenever one positron emitted, atomic number increased by 1 on the nuclei. That's why here F9 sorry, here one atomic number is decreased by decreased from that nuclei, so we can get F9 19. Okay, right. So plus 1 means it is taking up one atomic number, right? Okay, and next one here C16 sorry, C614 by the emission of beta particle. So this is beta particle, so minus 1, that means whenever beta particle emitted by the nuclei, one atomic number increases. Okay, so N714. So just remember that whenever nuclei emit positron, one atomic number decreases. Whenever nuclei emit beta particle, one atomic number increases. Okay, just keep these points in your mind. And next one, cis and trans complexes of the type platinum A2X2 are distinguished by simply Kurnikov test. So where thiourea used as reagent, cisplatin can use 4-thiourea and produce deep yellow colored complex. Okay, whereas transplatin uses only 2 equivalents of thiourea and the product is colorless. Okay, so cisplatin and transplatins are simply observed or differentiated by just using Kurnikov test. Okay, next one, the term symbol of molecule with electronic configuration. Just observe the electronic configuration here. Okay, right, and we need to give the term symbol for it. Just remember that always we need to look at the valence electronic configuration to give a term symbol. Okay, so here we have 1 pi u1 and 1 pi u1 as a valence electron shell, whereas first thing we need to find lambda. So for the first one, pi is equal to 1 and here pi is equal to 1. Now the total angular momentum, that is tailless lambda, is equal to, so simply we can use all lambda minus lambda to lambda plus lambda. So, okay, so for that for those two expressions we can get 1 and 0. Okay, the tailless lambda may be 1 or 0. So here if it is 0, that is indicating sigma. If it is pi, if it is 1, that is indicating pi term. Okay, now come to spin. So the first one, which is having 1 electron, and second one is also having 1 electron. So total for spin here, half and half, just take the sum of them, we can get 1. So total spin is 1 for the given electronic configuration. Now just substitute that in multiplicity. So 2 into s plus 1, we can get 3. Okay, right. Now, so we need to look at ungarrayed and ungarrayed subscripts. So whenever ungarrayed and ungarrayed, it result garrayed. Okay, right. And just remember that sigma is garrayed, pi is ungarrayed, pi star is garrayed, and sigma star is ungarrayed. Okay, and in that case ungarrayed and ungarrayed result garrayed. Okay, next one, a reflection under plane containing nuclei, that is minus into plus produces minus, and just remember that the minus plus indicated as a superscript on only sigma term symbol. Okay, so the minus and plus representations are not there for higher term symbols like pi, delta, okay, pi, delta, and more other, so that is other pi and tau. Okay, right. And in that case here, how we are getting minus and plus? As we said, reflection under plane containing nuclei. So here the first electronic term, that is simply electronic configuration 1 pi u and second one is 1 pi u. Okay, so they are representing px and py. Okay, from that molecular orbital diagram, if we take those electronic configuration, so we can get that these two electrons can be in px and py orbital. Okay, and just take for example, if orbital along the x here, now just take a plane and which is going through y and z. In that case, whenever we take the plane, plus is reflecting backside as minus, and minus is reflecting onto the plus, that means from the above or in front of that plane. Okay, in that case, anti-symmetric. So whenever the plane is reflecting anti-symmetric, then we can take minus. So it can be observed from character tables. Okay, so whenever it is anti-symmetric with respect to plane, then we can give -1. Whenever it is symmetric, then we can give +1 for it. Now just go to py, that is orbital, p orbital along the y axis, and already we need to take the same plane through the y and z. And if we take that plane, what is happening? Plane is going through the two lobes of the p orbital which is on the y axis. That's why here above and below of the plane you can see only plus and minus. Okay, that's why here it is symmetric. That's why here we can take +1. So minus into plus simply result minus here for the given electronic configuration. So here on the sigma, that means on the term symbol we are representing minus. Okay, the total term symbol is sigma grade and 3 minus. Okay, just observe it. Okay, right. Next one, a process is carried out at constant volume and at constant entropy. It will be spontaneous if. Okay, so here we know that from the second law of thermodynamic, delta S is greater than Q by T. Okay, so delta S is simply indicating entropy change, Q is heat and T is temperature, and we can also represent T delta S is greater than Q and consider it as equation 1. Now from first law of thermodynamics, we know that Q equals to delta U plus P delta V. Okay, so delta U is internal change, right? And from consider it as equation 2, from equation 1 and 2, so we can write T delta S is greater than delta U plus P delta V, or we can also write delta U plus P delta V minus T delta S minus less than 0. And from that, whenever we take volume and entropy as constant, that is equals to 0, then delta U less than 0. So third option is the correct answer for given problem. Okay, next one, the half-life of a zero order reaction A2 product is given by K is equal rate constant. Okay, so simply the first one, TF is equal to initial concentration of A by 2K is the correct half-life representation for zero order. Next one, for an aqueous solution at 25 degrees centigrade, the Debye-Hückel limiting law is given by. So this is log gamma plus or minus is equals to minus 0.509 Z plus into Z minus under root mu. Okay, here 0.509 for water at 25 degrees centigrade. Okay, next one, the microwave spectrum of a molecule yields 3 rotational constants. The molecule is, okay, here just look at some concept. Linear, whereas moment of inertia through x and y is equal, whereas through z it is 0. Whereas for spherical top molecules, the moment of inertia along x, y and z all are same. Okay, and if you look at symmetric top, here the moment of inertia along x and y is equal, whereas through the z it is not equal. Okay, and symmetric top molecules are two types, prolate and oblate. In prolate, moment of inertia along x and y are equal, and these two are greater than moment of inertia along z axis. And oblate molecules, oblate symmetric top molecules, whereas Ix, that means moment of inertia along x axis is greater than the moment of inertia along y and z. Okay, and asymmetric top molecules, whereas moment of inertia along x and y and z not equal. Okay, and for this the total energy is considered as Ex plus Ey plus Ez. Now we know that E equal to J by 2I. Here J is rotational constant and here I is moment of inertia. Okay, and from that we can say that three rotational constants along X, Y and Z. So three different rotational constants are observed for asymmetric top molecule. Okay, next one, the Q band in the vibration spectrum of acetylene is observed in the first one CC stretching mode, bending mode, and CH antisymmetric stretching mode, and second one CH symmetric stretching mode. So Q band in the vibration spectrum of acetylene is observed in bending mode. So whenever the linearity is changed, then Q band is observed for acetylene. Okay, right. Next one, the Stark splitting for a given field is larger for a molecule AX as compared to BX. Which one of the following is true? Here mu is dipole moment. Okay, and splitting of states by an electric field is simply considered as Stark effect. Okay, for any linear molecule, that may be AX or BX, in electric field, the energy of the state with quantum number J and Mj is given by, so just observe, HCB into J plus 1 plus a J Mj mu square E square. Okay, and here E is directly proportional to mu square. Okay, so from this you can see E is directly proportional to mu square. That means so whenever energy is more, so simply whenever mu is here, just observe. So here the Stark splitting for given field is larger for molecule AX. Okay, that is energy is more for that AX, that's why mu of AX is greater than mu of BX. Okay, next one, the adsorption of a gas on a solid surface exhibits the following isotherm. Which one of the following statements is correct? So here we have taken coverage versus pressure. So we need to look at Langmuir monolayer adsorption because the given graph or flat is representing that, and theta is equal to Kp by 1 plus Kp. At low pressure, theta is directly proportional to pressure. That is, whenever pressure increasing, the coverage also increases at low pressure, and it is first order. Whereas at high pressure, Kp, that means theta is simply equals to 1, and K simply here we cannot consider pressure. Okay, the coverage is not depending on the pressure. Okay, so you can see here, right? And from this analysis, and we can say that heat of adsorption or enthalpy of absorption is independent of coverage. Okay, so this is the assumption of Langmuir, that the binding site doesn't or has no influence on neighboring sites where the gaseous particles can absorb. Okay, so the first statement is correct one for given problem. Okay, thank you very much.